Hello everyone, my name is Rigel and today I'll be presenting a dynamic program for computing the joint CDF of order statistics. My collaborators are Cengke, Takehiro Oyakawa, and Professor Amy Greenwald, all from Brown University. As an overview, we will first be presenting the setup and motivation for our problem. We then summarize existing solutions to the problem before providing our own take. We will then show a few experiments comparing several of the aforementioned solutions directly. To finish, we will quickly summarize and provide some potential future directions in which to take our project. Okay, without further ado, let's jump right in. So, what is an order statistic? The kth order statistic of a dataset is defined as its kth smallest value. Some commonly seen ones are the minimum and maximum, which in a dataset of size n correspond to the first and the nth order statistics. Order statistics are also closely related to percentiles, for example, of median, 25th, and 75th percentiles, which are often included as summary statistics. In addition to their use in exploratory data analysis, order statistics naturally appear in various disciplines, including outlier detection, multiple testing, empirical process theory, signal processing, mechanism design, among others. In practice, order statistics are often used as a statistical measure. In many instances, the median is often preferred over the mean as a descriptive statistic as 1, it is fairly interpretable, 2, it is robust to outliers, and 3, its behavior is well studied, at least under ideal contexts. That being said, order statistics are less well behaved under more general settings, and their joint distribution can often be difficult to compute. To illustrate this complexity, we give an example. Consider this. You are the instructor of a large course of 100 students. This semester, your department has decided to combat grade inflation and mandated that at most 25 of your students can score A's or higher. Given historical student performances in your course, you must provide your students with an ex-ante cutoff score, X sub A, at the start of the semester, so as to comply with your department's mandate without completely deflating everyone's grades. So, how do we choose X sub A? Well, in this case, a straightforward approach to selecting X sub A would be to treat student performances as IID random variables and compute the distribution of the 75th order statistic at various candidate cutoff points. Sounds simple enough, right? Well, let's complicate the example slightly. We now assume that the department additionally requires that at most 50% of students get B's or higher, and at most 75% get C's or higher. So now, we must select cutoffs X sub B and X sub C in addition to X sub A. This problem becomes a bit trickier as our old approach of independently selecting a threshold no longer applies because the order statistics themselves are dependent, despite the random variables being independent. We can further complicate our situation by relaxing our IID assumptions on the random variables, for example, by discriminating between students who are taking the course for requirement and those who are not. We can also remove the independence assumption, as we can imagine that students who work in groups tend to have more similar scores, or we can simply just add more grade thresholds. Any of these will make the problem significantly more difficult. To begin to approach this problem, though, we must first formulate it rigorously. To do that, we'll need a bit of notation. So let X sub 1 through X sub n denote random variables distributed according to joint distribution F. And we let X sub k comma n denote the kth order statistic. We additionally have an index set C of size D, which contains the indices of the order statistics we wish to compute the joint CDF of at our bounds, small x. So the problem is then to compute the probability that for all j in 1 through d, the C sub jth order statistic is at most small x. From our example, this problem can become very difficult under the most general settings. Fortunately, there are a couple of assumptions on our random variables that can make our problem easier, such as assuming that they're identically distributed or that they come from a small number of distributions. We can also assume that they're independent. Alternatively, we can impose some conditions on our index set C, such as C being either very small or being the entire set of order statistics, and this can greatly reduce the computational cost. So which settings are we interested in then? Well, for starters, the IID, D greater than 1 case, is a good blend of practicality and complexity. In this setting, we simply assume that X sub I is distributed IID according to F for all I. What's nice about the IID case is that it generalizes naturally to the multiple distributions case. That is, let there be m homogeneous populations of independent random variables with n sub h random variables drawn from each population. Each of these random variables will have distribution f sub h according to which population they're drawn from. In our previous example, you can think of these populations as the students who are taking the course for your requirement and students who aren't taking the course for a requirement. In both cases, though, the goal is still to compute the joint CDF of the order statistics indexed by C at bounds small x. In particular, we wish to do this in time polynomial in the n sub h's and d, which are the population sizes and index set sizes respectively. In the next section, we will focus on the IID setting for the sake of notational simplicity. Okay, now we take a look at the combinatorial formulation of our problem and how our predecessors have approached the problem. In the conversion from the continuous to discrete problem, the key observation that we need to make is that the event that the C sub jth order statistic is less than or equal to the small xj is equivalent to the event that at least C sub j random variables are less than or equal to small x sub j. Furthermore, as the x sub i's are IID, we can think of them as indistinguishable balls. In addition, as the precise values of the random variables are irrelevant as we have independence, we can also think of the regions between consecutive bounds as bins. The problem now turns into computing the probability that for all j in 1 through d, there are at least C sub j balls, the leftmost j bins. Okay, so now some notation in combinatorial space. We define the space between the j minus first and jth bounds as bin j. This bin has corresponding probability p sub j, which is equal to the difference of the CDF f evaluated at the two endpoints. Now we let count j, which we denote here with big C sub j, to be the number of balls in bin j, and similarly count a through b as the number of balls in bins a through b inclusive. Lastly, we define bin condition j, which we denote as d sub j, as the event that at least C sub j balls fall within the first j bins. We extend that definition such that d sub 1 through j denotes the intersection of the first j bin conditions. Okay, so with the notation out of the way, we can formally rewrite the original continuous order statistic problem into a combinatorial one. One that we just need to compute the probability of satisfying every bin condition. Simple enough. And so far, our setup has been identical to existing methods. However, their approaches are doomed to exponentiality in D, and in some cases also N. And this is because many of the previous methods have just enumerated and then summed over all possible count configurations that satisfy the bin conditions. The issue with this is that the number of such configurations is exponential in D. And here we show a couple of the existing methods and their time complexities, as well as a couple of remarks. So the Papot-Begg theorem is the most general of the methods in the independent case for d greater than 1 and m equals n. The Papot-Begg theorem requires the computation of an exponential in D number of block permanents of size n, and each of these permanents requires exponential time in n to compute. So the runtime is going to be exponential in both. An improvement upon the Papot-Begg theorem, albeit still exponential in D, is given by Gluck for the case of independent D greater than or equal to 1, but m less than n populations. This is the setting for which our algorithm will become optimal for. Next, we have Bonsley Jr.'s dynamic programming algorithm, which also allows for dependencies between random variables. And this algorithm is notable because our insight can also be used to speed this algorithm up, though we will discuss this a bit more in the future work section. Lastly, we have the Bolshev recursion, which is a polytime algorithm, but requires strict conditions such as IID and D equals n, so the entire order statistic set. However, recent work has shown that this can be extended to the case where m equals 2. Our goal for today is to get the time complexity for the m populations d greater than 1 case as per Gluck's algorithm to look closer to the Bolshev recursion runtime. Okay, so now that we've explained the existing methods and their pitfalls, we now provide our own method which circumvents this exponentiality in D. We will first show the insight in our approach and then state the recurrence and algorithm explicitly. Okay, recall that our goal is to satisfy all of the bin conditions, D sub j. The key insight is that the bin conditions don't rely on the exact ball count in each bin up to j, but rather only the cumulative sum. So now we state that insight a little bit more formally. The probability of satisfying future bin conditions is the same regardless of conditioning whether on the exact configuration of the balls in the past bins or their aggregate. And from this insight, we can derive an important corollary for which our recurrence relation builds upon. So let phi of k denote the index of the largest bin condition d sub j that is satisfied, assuming that there are k balls in the first j bins. Then, the probability of satisfying the unsatisfied bin conditions phi of k plus 1 through d is equal regardless of conditioning on either the distribution of balls in the first j bins and the next phi of k minus j bins, versus just the total number of balls in both sets. Okay, and to provide a little bit more direction into how these results allow us to avoid having to track each of the count j's, we give a high-level idea of how our procedure works. First, we assume k balls are in the first j bins such that the first phi k bin conditions hold. We then throw enough balls into bins j plus 1 through phi of k plus 1 in order to satisfy the first unsatisfied condition, which is d of phi k plus 1. Next, having thrown a total of I balls in the first phi of k plus 1 bins, such that the first phi of I bin conditions hold, we can forget the configuration, as we only consider having to satisfy future bin conditions d sub phi of I plus 1 forwards, and this is due to our second, or our corollary. And lastly, we're going to repeat this process until all bin conditions hold. The important thing to note here is that we didn't have to track the individual counts, but rather only their sums at the intermediate steps. With this in mind, we now give our main recurrence. Okay, so assuming k balls in the first j bins, our main result states that the probability of satisfying the remaining bin conditions phi of k plus 1 forwards can be represented as the weighted sum of the probability of fulfilling the remaining bin conditions assuming I minus k balls fell into bins j plus 1 through phi of k plus 1. Here, the weights follow binomial distribution with a probability parameter given as a function of the p sub j's, which were the bin probabilities. And with our recurrence relation defined, we now give the formal algorithm with t of jk denoting the probability of satisfying the remaining bin conditions given k balls in the first j bins. The algorithm updates the entries of t in decreasing order of k, then in decreasing order of j. As there are O of dn table entries to update with each requiring O of n computations as per line 9, the space and time complexities are given by O of dn and O of dn squared respectively. In the M populations case, the only major difference in our algorithm made is that k and the counts are vectorized to represent the random variables coming from different populations. This will yield a space and time complexity which are still polynomial in the problem size. And to show empirically our space and time complexities, we plotted our algorithm's elapsed time on problems with either fixed population size and varying index set size, or fixed index set size and varying population size. We additionally used 3 different index set types, the first being the first few order statistics, the second being the last few, and the third being equally spaced order statistics. Okay, as these are log-log plots, in the second figure, the slope of roughly 2 for index sets 1 and 2 seemingly contradict the runtime of O of dn squared. However, this is because their time dependency in n is linear. And since n is at least d, we have that O of d squared n is still technically O of dn squared. And the same applies for the space complexity. In the space complexity experiments, we see the reason why index sets 1 and 2 grow slower in n but faster in d, as the table size is growing quadratic in d but constant in n. However, since we already know that n is at least d, we have that O of d squared is still technically O of dn. So our analysis holds. Okay, now we're going to do a little bit of side-by-side comparison with the existing methods. Here we have elapsed runtimes of our algorithm compared to Gluck's, Bonsolet Jr.'s, and the Papat-Begg theorem in the IID case. Here we let n vary from 6 to 30 and d from 1 to 5. And we notice that for small d, our method is actually comparable to the Bonsolet Jr.'s algorithm and the Gluck's procedures. However, for larger values of n and d, the difference becomes clear. The scientific notation also elucidates the exponential behavior in D that the other algorithms exhibit, as you can tell just by looking at the exponent. Okay, and to compare the runtimes for the case of two populations, so m equals 2, we compared our algorithm to Gluck's and found the same trend as before. The two procedures are comparable for small d, but the difference is clear for larger problem sizes. It is also worth noting that Bonsolet Jr.'s and Bapat-Beg's methods have time complexity independent of the number of distributions, and hence will have the exact same times as in the previous slide, whereas ours and Gluck's algorithms both slow down considerably. Okay, and now for a couple of closing remarks. So first, what did we cover today? Well, we transformed a continuous order statistic problem into a combinatorial one involving throwing a sufficient number of balls across various bins. Our approach dodged exponentiality in D by ignoring the individual count of each bin and only considering their sums when trying to fulfill bin conditions. This allowed us to improve the best known runtime of the M populations case from Gluck's, which is exponential in D, to one that is linear in D. And more broadly, our insight applies more generally, in particular to Bonsolet Jr.'s algorithm. At a high level, his algorithm maintains the distribution of the first I-balls across each bin and uses this to compute the distribution of the first I+1 balls across each bin. And it's so instead of tracking each C of I sub j, which is the number of the first I balls in bin j, we can instead track something like C sub I comma 1 through j, the aggregate sum. And then we'll spill over any of the balls from bins that are satisfied already to bins that are not. This allows for a drastic speed up, and we've already done a little bit of work looking into this. On a similar note, we can extend our algorithm to handle double-sided bounds on each order statistic. This would be relevant when computing robustness properties of sets of order statistics, such as, for example, constructing confidence bands around empirical distributions, kind of like in the DKW inequality, except now we have multiple points. This can be done by modifying the set of summation in our recurrence relation to prevent too many balls from landing in a specific range of bins, as now, in addition to lower bounding the number of balls that fall in the first j bins, we will also need to do the same for the last j bins. Okay, lastly, we must ask, how good can the algorithms get? Of all the existing methods, they are exponential in at least one of n or d, or in our case, m. Perhaps it might be possible to prove that the Bapat-Beg solution is as good as it gets. Or maybe we might even be able to reduce to a known NP-hard problem. In particular, block permanents are known to be NP-hard to compute. So we might be able to reduce it to having to compute a block permanent. Okay, before I finish, I would just like to thank the audience for tuning in, as well as our reviewers who have provided invaluable feedback. That said, that's a wrap. Thank you all again.